I'm going to try to roll it just slowly first time. So that's a little too slow. Okay, ready? That's unfortunate. Alright, apartment's not totally level. But that could still work. I got 4 different readings. You'll probably have to try it a few times in all reality. Okay. Oh, that's pretty good. Yeah, apartment's not level at all. Alright, then you just want to do it 2 more times at different speeds though. Okay? Alright. Ready? Now I'll do medium. Yeah, it's a lot better. Okay, now let's try one fast. Ready? Great. Alright, let's take a look at those results. Sorry, definitely don't have air conditioning. Let's see. I'm gonna share my stopwatch screen here. I believe that the last trial was a good one. I just want to look through it, just choose the best data to put into a graphing program is the idea. So let me bring up Desmos. Alright, graphing calculator. You're going to want to add a table. Alright, but you know where the markings were. 0 meters, 1 meter, 2 meters, 3 meters, 4 meters, and so on. Alright? Because I measured those off. But what you want to put in is your times of rolling. Let's see if I can find the slow data. I rolled it like twice with the slow. I can't just put in the split times though. Alright, so when I put my data in, these splits right here are what I put in, so I have to add them to get an elapsed time, right? So right now it's like a delta t, so I have to change it into just t. So we'll have 2.874, and then add the 1.51 makes 4.384. And then add the 1.572 and you get 5.956. Alright, that looks pretty good. Here's the data table to just put your results in. Estimate that uncertainty as best you can. I could put 0 and 0 there. My numbers were 1.469 here, 2.874, 4.384, and 5.956. Alright, now how off do I think they really are? It might be more off than just 5/1000ths. You know, like even though the stopwatch gives me a result to the thousandths place, I'm not super confident that I'm actually like that precise about it. So what I might do is I might say like, okay, I could be off by as much as like maybe 0.05 or even more, you know, a tenth of a second off on my clicking. That's probably reasonable, you know. So you might do that. But if you use that, then you'd want to just round your times to the same place value as your uncertainty. All right, so by that I mean you could round this to a 1.5 then. You know, this one could be a 2.9, 4.4 perhaps, and 6.0. All right, so that's good there. Let me adjust that in my Desmos table. All right, and then in Desmos, so I put markings down on the floor, which I thought were like a meter apart, but you know, maybe I was off. So maybe it was off by up to 10 centimeters. I mean, that's pretty extreme, but it's possible. So I'll do something like this. All right, so there's some data for the slow. Let me show you how to put error bars into Desmos as well, because you can do that. In order to get error bars in Desmos, what you could do is create a new column. All right, so here A1 represents the uncertainty in T, and B1 represents the uncertainty in Y. All right, so I'll just put those numbers in. Now at first, it's going to start to graph them like as if they were data points, you know. You don't want that though. So what you can do is just clear them, and they won't show up. Okay, then down below you have to tell Desmos to show the error bars. It says use x equals x1 times y1 minus b1. Okay, so what this is it's just telling it a range to make like a line segment with. But if you just copy that code, it'll do it. But one thing is, I'm going to switch my t back to x, but just remember x represents the time. And if you look closely, you can see there is like a little hatch mark that now represents the error in the position. So it's basically subtracting a little bit from each y value and then adding that same amount to the y value and just drawing a line segment. That's all it is. All right, and then you just want to do that with the y as well. And there you go. Now it's got some little error bars there. This can be done in Excel, of course, too. But I'm just doing Desmos in case not everybody has access to Excel. All right, that is that. Next, it says to create a regression line, like the best fit line for this data. So just do y1 tilde v x1 plus b. You can change color if you want. Let's make it like red or something. All right, there you go. Now, doing this type of regression is going to give you a slope and an intercept. The v is the slope of the line, the b is the intercept. So the slope actually corresponds to the velocity of this ball. And we can go now and fill in for the slowest ball what our regression equation is. Alright, so get your constants from Desmos. V is 0.67. And you can put the units in if you want. I'll put them in. Alright. And then my B was 0.01. Alright, there we go. Good regression equation for the slow ball. Now we could say what the speed was from the regression. So we'll say that the speed was 0.67 meters per second for that ball. Alright, and we just want to do that for the other balls too. So let me see if I can quickly grab that from the stopwatch. This one's not too bad. This last trial for the fast. I'm just going to take these 4, I think, as my data. Alright, you just want to go to Desmos, and I'd recommend just doing a whole new table for that. Alright, so a new X, new Y, and then just add in your fast. So 0, 0. Okay. 0.414. Zero 0.977. 1.541. 2.058. You can see the graph that it's making is different from the first trial. Alright, so we don't want to show those, of course. For data table 2, you just want to make sure that your subscript is like different from your first data table. Otherwise, Desmos will get confused. So I used a 2 for this table instead of a 1 that was used on the first table. Alright, then let's round off a little bit. 0.4. Let's say 1.0. 1.5, 2.1. Alright, just create your error bars now. Change these to a 2. Alright. Then type in your regression equation, which will be y2 tilde v2 and then x2. New equation, y equals 1.9 meters per second t plus it looks like it didn't like the B2, so I just came up with a new constant there, just C for it. 0.12. Next, it says we could calculate an average velocity for each ball. When you're calculating an average velocity, select 2 points, t initial, y initial, and t final, y final, with which to calculate the slope. We want the largest possible time interval for each ball. So use your leftmost point in each scatter plot and your rightmost point in each scatter plot. So when you do this, it's best to take your points from the best fit line rather than making them actual data points. But it says here you could just estimate it that way, which is fine. So for me, it would be 0, 0, and then for this recent trial, looks like we'll have 2.1, comma 4. All right, then we just want to calculate that slope. And let's see, we'll get that the slope is going to be the right y minus the left y over the right time minus the left time. Alright, so, yeah, there we get, 1.9 still. 1.9 meters per second for that. Alright, to construct an equation using those points, it says here you could use what's called the point slope formula. So that would just be y minus 0 equals 1.9 times t minus 0. So in other words, the equation is y equals 1.9t. You can plot that in Desmos. Y equals 1.9, but you gotta switch it to x. You can see how close they are, but the regression is better. The regression is the preferred way to do it, just so that's clear. Let's see. Now it says put your data in the average velocity column on the next page and repeat. Alright, so that's fine. We can just do that. Average speed was 1.9 meters per second. For the other one, we have 0 to 6. Yeah, 0 to 6 seconds. And that slope was 0.67. Alright, now you gotta decide, does it look like it's going at constant velocity? I mean, my trials were on a hardwood floor, and that matters. I would have done it on carpet, but my carpet wasn't really long enough. But if you can do it on like a little bit of a rough surface, that's even better. The reason why is there'd be friction. So it would cause your ball to slow down as time goes on. And then what would happen is, like the splits would get larger and larger. It would take more and more time for the ball to go from one mark to the next, Then you can see like a little bit of curvature to the data. I have a little bit of that possibly, but it's really tough to tell because it's hardwood floor, so there's very little friction. It's going to go pretty much with constant velocity. The next part is when you'll incorporate acceleration into the situation. So it says here, in the real world, friction and air resistance would slow a rolling ball down over time. And in the old days, people believed that there was some kind of like fluid that was transferred from person to the object that's rolling. And they thought that over time that fluid would lose its effectiveness, basically, It was believed that the natural state of objects was at rest. That motion couldn't continue unless there was that fluid there, that force. Isaac Newton said that isn't the way it is. He said that actually an object will continue moving unless it's acted upon by a net force. So in this case, the friction could be that net force that slows it down. In my example, there's very little net force. And when I do the parabolic regression, I don't even know if I'll be able to see the curvature of it. Hopefully you'll see a little bit of it. Anyway, to do the parabolic regression, what you do is you change your formula, because this formula is for constant velocity. Alright, so you just got to change it up. I'll do it in a new field here. So these are actually pretty good values. Pleasantly surprised to find that the acceleration is negative, because that's what you want. Let's try the same thing over here for the next one. Yeah, that one's pretty cool. Look at that one. That's good curvature. Alright, so turn that off. Yeah, so you can see like the slope does not remain constant throughout time. The best fit quadratic says that there's a concave down situation happening. And so the meaning of that in physics is if you got concave down position versus time graph, then you got a negative acceleration. And we can even see that our A value is negative. Alright, so when you go to write your regression equation, let's copy these over and then we'll decide upon the meanings of the physics variables involved, right? Alright, so we've got slow ball, negative 0.0064 t squared plus 0.71 t minus 0.02 or so. Then we got our fast equation, negative 0.13 t squared plus 2.16 t plus 0.05. Alright, so next thing you want to do is just determine what the acceleration is from that result. So the thing about the quadratic though is we want to match it up with what we know the formula to be for constant acceleration, which is actually 1/2 a t squared plus VIY t plus yi. That is just always the formula for constant acceleration. Now, why is that always the formula? It's good to know. It's because you start with the idea that you have a constant acceleration of some kind. Alright, so that constant acceleration is going to be called AY. For these examples, it's negative, but sometimes it's positive, depending on the situation. Next, you want to build it up through integrating to a velocity graph. You got to find an antiderivative of that. So how would we do that? Well, you'd say V is going to be the antiderivative of the acceleration, but that acceleration is just a constant. So when you build it up, you get that v is ay times t plus some constant c. But in this context, the constant c would be called viy, the initial velocity that the ball has. All right? Now for me, I did push these balls forward. So I gave it some initial velocity. Like, you don't start when the ball is at rest. You start after you gave it the push. So my velocity would actually start up here. But what's going to end up happening is it's going to go down in this example, because the velocity's slope is the acceleration. Since it's negative, we want our velocity to slope downward. And that, in some situations, could keep going. In our situation, it doesn't. We don't get that far. And not only that, but it just physically wouldn't make sense for the ball to reverse direction in this situation. But in some situations it does, like throwing it up in the air. Anyway, now you want to create a position function from this. So you got to integrate again. Alright, so the position is going to be the antiderivative of the velocity. So plug in the formula that we found so far. We had this, right? And you just got to find an antiderivative for each of those with respect to t. So you're going to get y equals, do an antiderivative of a constant times t, which will be 1/2 times that constant times t squared. Then do an antiderivative of just a constant viy, which becomes viyt. And then you got to put plus the constant c, of course, anytime you do an antiderivative. But in this case, the symbol yi, the initial position. Alright, now since you're rolling it from the start of your coordinate system that you established, you're basically rolling it from the origin to start. And it wants to head in the direction of the line y equals viy times t. And if there was no friction, no air resistance, then that's what it would do. But it actually deviates from that in reality. Instead, it makes a parabola. Now we want for our parabola to have its vertex coincide with where the first derivative is 0. And so this is where the ball comes to rest due to the friction, theoretically. But I didn't let it roll that long, of course. In my case, it just hit the cushion and I didn't get to see it stop. But I could extrapolate it to find out where it might theoretically stop, is the idea. Alright, so let's get our acceleration value for each of these trials. We're going to find that the acceleration A is going to be equal to 1/2 of A. You can see this in the formula, right? See, like right here, that term is in the place of the A. So what do you have to do? You just have to double your coefficient that you got here, is what you want to do. Alright, so that's going to give me negative 0.26 meters per second squared. That's my acceleration. Well, it's a deceleration though, because it's causing the ball to slow down. Over here it looks like we'll have .0128 or 0.013 meters per second squared. Now you want to interpret what the initial instantaneous velocity is from your quadratic as well. So this one's the acceleration, which corresponds to the red graph over here. Alright, so that's just a negative 0.26 for that one trial. But now you want to find what was that initial velocity that you rolled it with, VI. So now you want to look to this number. Alright, so 2.16, and the units will be meters per second. Here you don't have to do anything to the number because VIY just is in the place of B. Down here it was 0.71 meters per second. Initial position 0.05 meters and 0.02 meters. All right, so that is that. So check this out. I said earlier that according to regression and just taking an average slope, well, I said that the speed of the ball was 1.9 meters per second, but that is an average for the whole thing. And then so is this, an average. But check out the values you get with the parabolic regression. They're different. Here it says that your actual initial velocity was substantially higher than what we thought because of the curvature to it. So it's because it's got a steep slope here. So there's a difference between the initial speed that you get from the tangent line here than you would have got from the tangent line out here. That's because the ball is slowing down. You can also see this by the velocity values, how they're high at the start and then they're small toward the end. So the idea is that the velocity is decreasing. That's what you want to look for. Alright, hope that all makes sense. Let's see, here it says the time derivative of an instantaneous position function is called the instantaneous velocity function. We want to get an instantaneous velocity function from our results above. So y prime is also known as Vy. Vy is, for me, negative 0.26 t plus 2.16. What I'm doing is I'm basically taking the derivative of this. So if you take the derivative of that, you get this. And here the values have meaning as well. The 0.26 is of course the acceleration, but the 2.16 is the initial. So that's something you want to put right here. Now though, you want to use it to predict what the final velocity is at TR, which is your last time reading. So I got to go back to my data. For the fastball, this is my data. My last time reading is the 2.1. That's when the experiment concluded, basically. So what we want to find now is plug in 2.1 seconds into this formula. to see what velocity you end up with according to the regression, right? So I get 1.61 meters per second. Now, what was the average velocity from the other page? Let's go back. 1.9. So isn't that cool how the average is between the two extremes? So this is my start, and I didn't let it go all the way till it stopped on its own. I only let it go so far. So let's say from here to here. Somewhere in the middle there's an average velocity. And so my values say that I start off with 2.16 and my speed goes down to 1.61, and then somewhere in the middle is approximately 1.9, which is my average. But yeah, that's the basics. Assuming acceleration is constant, verify that the formula here holds. Alright, so for my fastball, 2.16 was my starting velocity. We want to add that to 1.61, which is my ending velocity. And then divide by 2 to get the average, it's called. Alright. Comes out to 1.89. Basically 1.9. And lastly, can we extrapolate it to find out where would the ball come to rest of its own volition, assuming that the acceleration was constant? So for that, I would go to my velocity function. I would have a t plus VIY. Plug in my numbers. For the fastball, it's negative 0.26 t plus 2.16. You just want to set that equal to 0. Say, when does the derivative become 0? That would be, of course, extrapolating it to this point when the thing comes to rest. Alright, so solve that, and then you're pretty much done. T equals 8.3 seconds. Now you could go to Desmos and just see if that checks. You could click right on the vertex of a parabola and say an 8.0. I suppose it could be due to rounding, the difference there. 8.3 versus, because I did round off a little bit in my constants, but you just need an approximate time when it comes to rest.